Okay, welcome to linear programming practice. Your problem here, we're going to get a system of inequalities, find the intersection points of all of these inequalities, and shade the appropriate solution region. So here's the example. You are about to take a test that contains questions of type A worth 10 points and type B worth 25 points. You must answer at least 3 of type A, but time says that you can't answer any more than 12. You must answer at least 4 questions of type B, but time restricts answering more than 15. In total, you can answer no more than 20 questions. How many of each type of question must you answer, assuming you get them all right, in order to maximize your score? And then, what is that maximum score? Let's first start by defining some variables. Okay, so what would be some good variables for us to use? Well, we have questions of type A and we have questions of type B. So maybe we go ahead and let's go with the black pen. Maybe we go ahead and let x equal the number of type A questions that you answered. And then maybe we can go ahead and let y equal number of type B questions answered. Okay, so now we need to go ahead and set up these inequalities, also known as the constraints of the system. So we're going to set up some inequalities here. And let's start with the type A questions. We know that we must answer at least three of type A. So we know that A has to be greater than or equal to 3. But it also does tell us that we can't answer any more than 12, so A must also be, let's see, can I answer 12? I can answer 12, but I can't answer more than 12. So I can be equal to 12. So there's my constraints for the type A questions. And then similarly, let's go ahead and put some constraints in for type B. What are some good constraints for type B? I know you're thinking about it. Why don't you try and put down something that you think is right? I'll wait. Alright, let's see what you have, and now let's compare that to what I have. You must answer at least 4 questions of type B, so B has to be greater than or equal to 4. But time says you can't answer any more than 15, so it has to be less than or equal to 15. Now, you think it might be done, but there are still some more constraints out there, and you might be able to see it. Wrong color. Let's go with black. And so in total, you can answer no more than 20 questions. And since X is the number of type A questions answered and Y is the number of type B questions answered, why am I using X and Y? I should use A and B. Anyway, let's continue going on with A and B. I know that A plus B then has to be less than or equal to 20. No more than 20. It can be 20, and it could also be less than 20. So now I have my constraints. So now I can get to starting to graph these inequalities on a coordinate plane. And then I can answer the questions involved. Okay, before we go ahead and start graphing these inequalities, we do need to determine the max-min equation. In all linear programming problems, the intent of the problem is to be able to maximize or minimize, depending on the context of the question, a certain value. Sometimes it's profit, sometimes it's scores, it could be anything. So in this case, we want to determine the maximum or minimum equation. So our score in this problem is going to be equal to, let's see, type A was worth 10 points. So if I do 10 points multiplied by the number of type A questions I get, and then I add to that, how many points is type B worth? Let's see, 25. So B is worth 25 points. for every type B question I get, this is going to be the equation that I use in order to maximize my score. So I'm going to try and plug in numbers for A and B and see which one gives me out the largest score. Now, because I don't want to just choose randomly points for A and B, that could take forever because there's an infinite number of them, I'm going to use strategic points for A and B, and those happen to be the points of intersection of the system of inequalities that we just decided on for our constraints. Alright, let's go ahead and graph these inequalities. I'm going to grab a pen here. I'm also going to need to get lines too. Alright, so there they are. Alright, first thing I need to do is graph A is greater than or equal to 3 and less than or equal to 12. So I'm going to put a solid line at A equals 3 and a solid line at A equals 12 and shade everything in between. Alright, let me move this down a little bit. Now A, we don't have an A-axis or a B-axis, but we just need to identify which one's going to be which. So let's go ahead and call this axis the A-axis. So this will be the A-axis, and this one will be the B-axis. So now when I graph A is greater than or equal to 3, I have a line to put it on. So here's where A is 3. Here's everywhere that A is 3. And let me do the same thing for where A is 12. I think that was the problem. Okay, yeah, 12. So there's where A is 12. And now I'm going to shade everything in between. Let's go with a creative pen and do this one here. So everything in between. I don't want to go past the line. But the lines are part of the solution because they're solid, and they're solid because it can be equal to. Alright, so there's two sets of constraints. A is between 3 and 12, inclusive. Now let me do the same thing for B. And let me get some lines here. Now for B, we have B has to be between 4 and 15. Here's our B axis. So let's go ahead and graph the 4. Let's go ahead and graph the 15. And then we want to shade everything in between there. So let's get a creative pen here. Let's go with, come on now. Let's go blue and red or whatever this is. And I want to shade everything in here. Oh, it's going to go right over that. We're not going to necessarily see the intersection area this time. Maybe I'll use crayons again next time. Alright, so almost done. Almost done. We do have one more constraint that we need to graph, and that is the A plus B has to be less than or equal to 20. So if I wanted to graph A plus B has to be less than or equal to 20, well, let's see. The y-intercept is 20, or the b-intercept. The a-intercept is 20 also. And the slope is -1. So I think I can get that all the way down here. Let's draw that line. So it's going to go from there to there. And I want to shade everything that has A plus B less than or equal to 20. And that includes 0, 0. 0 plus 0 is less than or equal to 20. That makes it true. Alright, I'll go highlighter here. That might be a better choice from now on. So everything this way. I lost some lights there. Lost some part of the line there. But I'll clean that up. Alright, so let's go ahead and touch this up as far as where is the shaded region for everything. I think the smiley faces worked well last time. So there's a corner point, there's a corner point, there's a corner point, there's a corner point, there's a corner point. So I want to shade everything in there. So let's go ahead and take the stars. So this whole region right here is our solution set. It means any point in here will make every single one of those constraints true. All 5 constraints. And yes, there are 5 of them. So if I want to now take all of those points that I just shaded in and plug them into my score function in order to maximize or minimize, I would need to plug in every single one of those points into this 10a plus 25b and see which one gives me the largest number. Now, that is an impossibility because there are an infinite number of points. So what we do instead is we know that the maximum value is going to come from one of these smiley face points, from one of these vertices, from one of these points of intersection. If there's going to be a maximum value here, it's going to come from one of these, what is it, 5 points? 1, 2, 3, 4, one of these 5 points. So the first thing we need to do right now is find the ordered pairs that represent these 5 points. Let's see if you can do that now. Find what the ordered pair is for this point right here on the upper left. So what is that ordered pair right there? Go ahead and take a minute and see if you can find that out. So hopefully you realize that the intersection point for this first smiley face is at the intersection of this vertical line x equals 3 and the horizontal line y equals 15, therefore making the intersection point the ordered pair 3, 15. And all the intersection points of the vertical and horizontal lines should be pretty easy to find. So if I look at this one down here in the bottom left hand corner, finding the intersection of that smiley face, that's pretty straightforward, as it's the intersection of the vertical line x equals 3 and the horizontal line y equals 4, therefore giving you the ordered pair 3, 4. So let me call that point B. So point B is at 3, 4. Go ahead and find this third intersection point of a vertical and horizontal line. Okay, point C then. Hopefully you've had enough time to figure it out. You could always put me on pause if you need more time, don't forget. So that has an x-coordinate of 12 and a y-coordinate of 4. And then moving along to point D. Now, here's where it gets a little tricky, but not too much. We already know how to find the intersection of 2 lines. It happens to be the solution set. So if I were to remove everything else from this graph, let's get rid of everything here and just focus on what we want to do. We want to find the intersection of just these special lines here. So I don't need this. Let's get rid of that. Delete. Let's get rid of that. Delete. Delete. We don't need this one. Delete. So if I want to find just the intersection of these 2 lines right here, so I want this intersection point right there. Whoa, that's not what I meant to do. Undo. The intersection. Oh, erase. Oh my gosh, look at that. Alright, let's try it again. I want to find the intersection point. Okay, so now we're going to find this. Oh boy. Redo. Undo. Normal pen. Come on.